So we are going to start our pure year 2 differentiation, which is an important chunk of work on its own, but most importantly it leads us into year 2 integration, which is where, if you found trig tricky, it's probably where you'll find that's the other place in the syllabus that's tricky. You know, well, it's all hard, but you know, I think integration in year 2 and differentiation and trigonometry in year 2 are the two really sticky bits. So I'm keen that we get through this as quickly as we can. Hence the fact, you know, I'm really delighted that I'm going to see you 3 times this week, which is brilliant. There we go. So anyway, here is a year 1 differentiation question, slightly different. Normally you're asked to find the gradient at a particular point. Here they're telling you what the gradient is. They're saying the gradient is 9, and you've got to find the point where it has that gradient. So I'm hoping you're going to differentiate this and not make x equal to 9, but you're going to work out what value of x makes it equal to 9. There we go. And then you've got a tangent and a normal to work out. So this is nothing new here, nothing new. Multiplying by the power, reducing the power by 1. Multiplying by the power, reducing the power by 1. Calculator?
Yes, please. I don't even know how I don't have it. I don't even use it the whole way.
You're perfectly okay using your calculator, but this one actually factorizes quite nicely. You'll get 2 points, but it says in the question x is greater than 0, so that allows you to narrow it down. The gradient is 9. That's what f dash of x equals 9 means. So when you come to do the tangent and normal, the gradient of the tangent will be 9. So that's how you do that process. to get the y value, you go back to the original function. So once you've got, and you didn't have to do this, you could have just whacked that into your calculator, got the same answers. Just keep my factorising skills loose. You all right, Mr. G?
Remarks.
Oh, there you go. Well, if you have you emailed Barry or shall I do it?
Well, it's just like that, so I had to scan it all. So I just took the pages out.
Okay, well, yeah, no, if you look at the email, all I've done is said, I've emailed the full paper to you.
Yeah.
And I said, please print pages 1, 2, 3.
I'll do that then. I'll
Yeah.
pages to print.
Yeah, and page is not question mark, question mark.
Yeah.
And including page mark.
Because then I've gone through and edited so it says the right thing on it.
Oh, you've actually.
So it says, so change each question to it.
Right, okay, I think.
No, Barry can do that.
No,
Just piece like that.
He's got the ability,
So,
brilliant. If you could just send us.
took every other page out to start with.
Yeah, I've got 54 marks, so there you go. We've both done very well. That's I think it's 3-3, is it? This is good because it's it's practicing lots of those techniques that we've done. The use of the plural in part A doesn't mean we're looking for 2 points. So, so the coordinates, those are the coordinates of 1 point. That's perhaps a bit misleading. Tangent, that process that, well, it's probably a bit rusty, but I'm hoping it's something that you're really familiar with. Gradient, point, 3-step process. Write down the y equals mx plus c, replacing m with the gradient, then substitute the values of your point in to work out c, and then thirdly, rewrite your equation. And then Pat, what's the gradient of the normal going to be?
I'm not sure. I was actually about to ask you.
Do you remember the little trick? Our secret math sign?
-1/9.
-1/9, that's right, yeah. So it's the perpendicular gradient. So straight away we know this isn't going to be anywhere near as nice. but we are told how to write it. So if I just give you a couple more minutes just to see if you can get somewhere with that. I'm pretty confident, but at some point I'm going to be multiplying by 9 to kill the fractions, but I'll let you see how far you want to get first.
Yeah, well, that's it.
So I get y is minus 1/9 x plus c. Substitute in 3, 3. So I get 3 is equal to minus 1/9 times 3 is minus 3/9, which is a third. So if I add a third to that, that's 3 1/3, which is 10/3. So I get y is equal to minus 1/9 of x plus 10/3. And now I'm going to... Yes, sorry.
Could I have more reflected, please? Mine's just going.
Right. I have a slight problem because that one is dead as well. So let me see. Right, another one. Dead as well. Yes, you're very kind. I'm sure I'm going to find one here that is working. There we go. There we go. That's all good. Thank you, though. Right. There we are. I'm going to multiply by 9, so that's going to give me 9y minus x, and that's multiplying by 3 and then by 3 again, so that gives me 30. And then it wants me, I've moved it on now, but it wants me to shovel everything onto one side, so that was my answer for that third one. So we had a differentiation question that led into a tangent and a normal. I mean, you're unlikely to get a question where you're asked to find the tangent and the normal, but there we go. So I mean, that's all rusty perhaps, but hopefully there was nothing too new there. So what are we going to do as part of this year 2 pure? Well, I want us to talk about the second differential, which is either called dy by dx squared or f double dash of x. We've come across this before, and we came across it in questions like this one, where we have to find the turning points or the stationary points. Cubic, so I sort of know, and it's a happy cubic, so it's going to start low and end high. So I'm expecting there to be a maximum, and a minimum. But I can use differentiation to find it, and I can use the second differential, f double dash of x in this case, to work out which of my turning points are maximums or which are minimums. So have a go. See if you can differentiate it. Remember, when we find stationary points or turning points, we ask, when does dy by dx or f dash of x equal 0? When does the gradient equal 0? So that's our starting point. And then once you've found those turning points, we're expecting 2, there are 2. Differentiate again and see if you can work out whether they're maximum or minimum. although the question doesn't say it, differentiate again once you've found your turning points and investigate whether they're maximum or minimum. We should know. We know what a cubic looks like, so it should be something we can sort of work out without doing this, but we're just confirming it. I remember substituting into, because you've got to substitute your x values into your original function, really easy if you use your calculator. Yeah. Set the value to x and then type in the function, and then go back and change the value of x. With the second differential, we're only interested in whether it's positive or negative. We're not interested in the actual numerical value. And then you've got to remember what that actually means. What does a positive second differential? What does a negative one mean? So I'm hoping you found turning points when x was 1 and 3. And again, I've done that. You could just use your calculator at that point to get your 3 and your 1. Substitute into the original function should have given you 1 and 5. Second differential, when x is 3, 6 times 3, 18, take away 12 is positive, which if you remember tells us that that is a minimum point. When the second differential is less than 0, that reminds us that that stationary point is a minimum. Hang on. Greater than, sorry. Minimum. Greater than 0 is positive, isn't it? I thought so. And then when x is 1, 6 times 8 is negative, which tells us it's a maximum. So if the second differential is less than 0, then that reminds us that that is a maximum. And that's what the curve looks like. And so we've used the second differential to confirm that this point here, 1, 5, was in fact a maximum, and this point here, which is 3, 1, was in fact a minimum. And the second differential tells us that because what we're doing is we're differentiating our equation for the gradient. So that's telling us about the way the gradient is changing. And so look at what happens with a maximum. Here the gradient's really big, it's positive. Here it's still positive, but it's a bit smaller, so it's got smaller. Here the gradient is 0, and here it's negative. So as you move through a maximum, the gradient is getting smaller. So the gradient of the gradient, it's downhill. If we plotted the gradient rather than the function itself, it would have a downhill, it would have a negative gradient. And that's why when you have a second differential that's less than 0, that shows us it's a maximum. But actually, it isn't just negative here. For this whole period, while the gradient is going from something very big to something very negative, d2y by dx will be getting smaller. So we'll get a negative value of d2y by dx squared, or f double dash of x, they're the same thing, for that whole period. So if I substituted in a different value of x, I'd still get a negative d2y by dx squared. I'm just going to shrink this down so that I can see the whole thing rather than... And so actually a negative second differential doesn't just indicate a maximum, it indicates that we're dealing with that point with a curve that's sort of going like this. And sort of going like this has a name. It is called concave. A function or a graph is concave if its gradient is getting smaller. So for this period, from all the way down here, all the way around there, the gradient of that curve is getting smaller. And we call that concave. We call that concave. So the gradient is getting smaller. And what about this bit here, this minimum? Well, for all of that period there, not just at the minimum, but for all of that period there, the gradient's getting bigger. The gradient's getting bigger. It's very negative at this point, gets less negative, 0, and then starts getting positive. It's getting bigger, and we call that, unsurprisingly, convex, where the curve is convex, the gradient's getting bigger. Now, I'll be honest with you, I sort of feel these are the wrong way round. I want that to be concave and that to be convex. And so it's one of those things that I just remember it's the wrong way round. But Matt in the other group was he said, yeah, all you need to do is look at from the bottom of the picture. So looking from the bottom of the picture, yeah, that's concave, it's caving in, isn't it? And that's convex. I think mirrors when I think of concave and convex. So if you're looking from down here, that's a concave mirror and that's a convex mirror. Yeah, I think that's probably better than saying it's the wrong way round. So something must happen then around here. The gradient's got to stop getting smaller and start getting bigger. It's got to move from being a concave curve to a convex curve. And at that point, d2y by dx squared would be 0. There is a point here where the gradient stops changing, just briefly. And we call that point a point of inflection. Now, we've come across points of inflection before, because sometimes turning points can be points of inflection. So sometimes you find a turning point, and when you evaluate the second differential, you get 0. Not positive, not negative, it's not maximum or minimum, but an inflection. For example, x cubed. That's a turning point in x cubed, but it isn't a maximum and it isn't a minimum. And it's a point where the gradient stops getting smaller and starts getting bigger. So a turning point can be an inflection, but an inflection will not necessarily be a turning point. This one here is not a turning point. The gradient does not become 0. But it is important that we realise that somewhere along this line we get a point of inflection where the curve switches from being concave to convex. And a point of inflection can be found because it's where the second differential equals 0. So should we just check? I mean, it looks like it's around 2. Let's just see if we can find it exactly for that curve. So we're going to differentiate it once. Well, we've already done that. Not going to worry about turning points. We're going to differentiate it again. Already done that. 6x minus 12. Ask, when does that equal 0? So we're not looking for turning points now. So to find the inflection, or to find an inflection, ask when f double dash of x or d2y by dx squared equals 0. And just do it for that. So that's the same curve that we just differentiated. So that confirms it. There is a spanner in the works though. A point of inflection will always have the second differential equal to 0, but not every place where the second differential equals 0 will be a point of inflection. So if it's a point of inflection, d2y by dx squared will be 0, but if you find somewhere where d2y by dx equals 0, it's not necessarily a point of inflection. So we just need to be careful. So I need to write that. Not every place point where d2y by dx squared equals 0 will be an inflection. How, therefore, do we find whether it is an inflection or not? Well, we have to look either side of the point just to check. And I think that's best illustrated with an example rather than So not every point, sorry if you're on video or if you're here, it's very hard to read, I apologise. I'm rusty after Christmas. Not every point where d2y by dx squared equals 0 will be an inflection. We need to look either side of the point that we found to check. And I want to illustrate that with an example. So here is another function. It's a quartic, which we know can be a bit weird and wacky. And we're not being asked to find the turning points, stationary points. We're being asked to find points of inflection. So we're going to differentiate once. It's y equals, so that will be dy by dx. But then we're going to differentiate again. And we're going to ask, when does d2y by dx squared equal 0? So when you're looking for turning points, you ask, where does dy by dx equal 0? If you're looking for a point of inflection, you go again and ask, when does d2y by dx squared equal 0? And then I'll illustrate this thing about looking either side just to confirm that they are points of inflection. Yeah, I did it. What have I got? Oh, for goodness sake. God. I did exactly the same question this morning and got a third and minus a third. That's why I was thinking, what have I done wrong? Right, divide by 2. Actually, that's the difference to 2 squares. So you could factorise it as 3x minus 1, 3x plus 1. Anyway, we've got our two not turning points, 2 inflections at minus third and plus third. So these are the points where it stops going like that and starts going like that, or stops going like that and starts going like that. They're not turning points. Now, okay, the question says that there are 2 points of inflection, so, and we only found 2 points, so we're pretty sure they are. But let me show you how we can check. So I have got my values of x. I've got minus a third and plus a third, and I know that at those points d2y by dx squared is 0. So I'm just going to try points either side of that, just to check that I am going from convex to concave or concave to convex. So, you know, well, a point between minus 1/3 and plus 1/3, a nice easy one, would be 0. And a point the other side of that would be minus 1, and a point the other side of that would be plus 1. It doesn't matter really. You know, I've chosen nice easy values. So if I go back to my second differential, 18x squared minus 2, where x is 0, that's going to be negative. Negative, it means the curve is concave at that point. So I'm hoping to find that this is positive, and this is positive, because that will confirm these are points of inflection, where it goes from convex to concave and then back to convex again. Let's have a look. So when x is 1, that's going to be 18, take away 2, that's positive. And minus 1 squared will also be 1, so yeah, that's positive as well. So what it tells me is that this curve goes from convex, which is like that, through a point of inflection to concave, and then back to convex. I haven't found the location of these turning points. If they are there, it might just be gradually changing rather than actually being a turning point. But that's what that has confirmed. So it's confirmed that these are points of inflection because they are points where the graph changes from convex to concave. I've confirmed that by checking that dy by dx either goes from positive to negative or from negative to positive.
Can you explain that again?
Yes.
There you go.
So the points of inflection are the points where the curve changes from convex to concave. So in the first example, this is concave, this is convex, this is the point where it stops being one and starts being the other.
Mm-hmm.
When a graph is concave, because its gradient's getting smaller, d2y by dx squared will be negative, and when the graph is convex, d2y by dx squared will be positive. So there must be somewhere in the middle where it's, if it's gone from negative to positive, it must be 0, and that's what the point of inflection is. So in this example, we found the places where d2y by dx squared was 0, and I just then looked either side of those x values just to see, right, what was happening to the curve either side of that. When I made x equal to minus 1 in d2y by dx squared, the answer was positive, which told me it was one of these, convex. Now we don't know the actual shape of the curve, but we know a little bit more about it. Let's have a go at a couple of other questions. So here in these first two, we're asked to find where the graphs are concave. Concave, so we're asking where is the second differential less than 0? So we're going to differentiate dy by dx. We're going to differentiate it again, dy by dx squared, and we're going to ask when is that less than 0? So we're going to get an inequality. The first one's quite a nice easy inequality, the second one's a little bit fiddly. good news about the second differential is that it always gets easier. The powers of x get smaller, don't they? So don't stop at the first differential. We do that if we're finding turning points. We don't care about turning points. We just want to know when the graph is concave. These questions aren't asking for the inflections, they're asking when it's concave. So not when does it equal 0, but concave, that's when it's less than 0. So we've got a point of inflection when x is 5, it'll be negative when x is less than 5. So I got my second differential and I asked when is it less than 0, not equal to 0, added 5 to both sides, so that told me that it's concave when x is less than 5. Start the next one if anyone's ahead of me.
Do you flip the sign when you square root?
No, right. You've got to be careful when you square root. It's not a flipping sign thing, but you're absolutely right to be cautious. So what we're asking is, when is that less than 0? So divide everything by 4. So you sort of got to something like that. Yeah, this is an interesting one, isn't it? We want to know for that second one where the second differential is less than 0. And there's a couple of approaches you can use. You could think, right, I'm going to sketch this. This is one way of solving a quadratic inequality. I'm going to sketch that, plot it on your calculator, and it'll look, oh no, hang on, it's unhappy, isn't it? Negative x squared. It'll look like that. And you can just ask, so when is it less than 0? So it would be here and here. So it would be when x is less than that value and bigger than that value. That's one way of doing it, solving it graphically. Or you could solve that using your calculator and get the 2 points where it equals 0, and then you know that it's less than 0 here and here. If you carried on to here, you've got to say, right, when is x squared bigger than 2/3? Well, you don't need to flip the sign when you square root, but you've got to think, okay, so that means x, it's something to do with the square root of 2/3. Certainly, if x is bigger than the square root of 2/3, then x squared will be bigger than 2/3. That's certainly okay. But you could also have minus the square root of 2/3, because when you square that, it'll become positive. And the trouble with that is, if you have a minus number, the more negative it is, the bigger it is. So the other solution is x is less than minus the square root of 2/3. So it wasn't just about flipping the sign, it was just about being very careful at that point about how you proceed. So the graph is concave, these two, dy by dx squared is less than 0, after x is 2/3, after x is the square root of 2/3, and before x is minus the square root of 2/3. Now, could I encourage you to have a go at this final one ahead of tomorrow? I'm interested to see how you get on with it. What I propose you do, and it's not the only way of doing it, but with this one you find the points of inflection. So you differentiate it again, and you ask, when does that equal 0? That will tell you about the points of inflection. And then you could look either side. So you hopefully find that, either before one or after another, it'll be concave or convex. So it's a bit like the first question that we did, where we found the points of inflection and then we checked in between. There are other ways of doing it, but yeah, we'll start tomorrow's lesson.
Write it down.
Yes, I'm not going to take it away. Start tomorrow's lesson. I'll have a look at that. Yeah. Yes. Almost certainly. So for those not here, we'll start this in the next video.